So that kind of addressed a little bit the topic of, what's an optimal amount of protein at a meal. But then the other question I always thought about was frequency and distribution. When we talk about protein intake, we just give a daily number, okay? But protein metabolism is regulated on a meal-to-meal basis. And most Americans actually consume about 60 to 70% of their protein at one meal, which is dinner. If you think about what the normal American usually eats, it's a cereal for breakfast, bagel, something like that. Lunch might be a little bit more protein, a sandwich or a salad or something like that. But then dinner is really, they'll have 10, 12 ounces of meat, something like that. They'll get 50, 60 grams of protein, and that will be the majority of their protein. Well, can you make up for low protein at other parts of the day by overeating it at another time of the day? That's also important. That's a question we had. Actually, it was funny. I was drafting up my final experiment to Dr. Layman, and in every single one of my reviews I'd written something about protein distribution. He said, "You realize you talk about this throughout your thesis that you're writing, and you've never actually tested it." I was like, "Oh, I guess I better test it." So this is actually a graph taken directly from him, where we thought about the threshold response. So what if you have a theoretical optimal protein distribution where you hit the threshold at 3 meals versus a theoretical unoptimal protein distribution where you are below the threshold at 2 meals and way above it at another one, kind of like how most people eat, right? So what would that actually make a difference? Theoretically, we say yes, but it's always important to test things. So we designed a diet groups. Actually, one of the big criticisms I got from the comparing wheat, soy, egg, and whey was people said, well, you can't say that it's leucine that's causing this because there are other amino acids in protein, even though none of the other amino acids had ever been shown to do anything metabolically for muscle protein synthesis. But that's neither here nor there. So I said, okay, well, let's take the highest quality protein source, whey, and let's distribute it based on what we know about the threshold and see if we can make it act like a lower quality protein source by distributing it inappropriately, okay? So we did this experiment in rats again, but it's actually been, I believe Doug Patton Jones has repeated this in humans. And so what we gave was breakfast was twice as much. So we have an evenly distributed whey group and an unevenly distributed whey group. Breakfast was twice as high in protein in the evenly distributed group and an amount that we knew would hit the threshold. Okay, it would be sufficient to start muscle protein synthesis. Whereas the unevenly distributed whey group, we knew it would be below the threshold. Okay? Now, it's not truly evenly distributed because dinner's still a little bit heavier because they had a total, their calorie intake at their dinner was bigger overall because we still wanted to make it kind of similar to the way people eat. They eat bigger dinners regardless. So it was a 1 gram protein at dinner and then 70% more protein in the unevenly distributed group. But the total for the day was the same. And again, same thing for leucine. Total for the day was the same even though it was distributed differently, okay? So what we found is that this is after the breakfast meal. Like we thought, below the threshold for unevenly distributed whey, you got a little bit of a response, but not much, whereas you got the response you expected in the evenly distributed group. And then this is, remember I talked about one of those big named initiation factors, S6K? So this is just basically showing that this makes sense, because S6K had the same response. So we also, we fed these diets for 11 weeks, and then we took out muscles from the animals and weighed them to actually see if there were differences. So we looked at the signaling to see if the signaling was there. The signaling was there. And that signaling, we measured again in 11 weeks, and it was the exact same. Okay, and then we looked at tissue weights. Significantly bigger muscles in the animals fed evenly distributed whey versus unevenly distributed whey. Okay? And let me back up real quick. The interesting thing was their body compositions weren't different. Okay, their body fat levels weren't different and their lean body masses weren't different. And I was like, well, how do you explain that difference if there's no difference in? And what a lot of people get hung up on lean body mass is all non-fat tissues, skin, bone, organs, liver, heart, all that sort of stuff. So we started looking at some of the other organs. Well, in the unevenly distributed whey groups, they had actually bigger livers versus the evenly distributed whey. So when you change the distribution of a protein source, you don't necessarily change lean body mass, but you change where those amino acids are targeted for storage. Does that make sense?
What do you think that is? Does it seem like an odd response? I wouldn't have guessed that, I guess.
Yeah, I think if I had to hazard a theory, one would be the liver kind of acts as a sink for extra amino acids.
Sure.
And maybe the thresholds are different in different tissues, right? So the threshold in muscle may be quite different from the threshold in liver. So I think that's why you might see difference in responses.
It was actually higher in the undistributed group, right, versus evenly distributed?
Right, exactly. Liver weights were bigger. So basically showing that when we published the paper showing there's no differences in body composition, this is why, because it was no differences in lean body mass, but amongst the individual tissues, there was differences.
So if you were to look at other organs, do you think it would be different?
I wish we had. The problem was we didn't save a lot of the other organs because this was not something we expected. And we didn't know it until afterwards. And some of the only other organs we had was liver and kidney wasn't different. So I don't know if I would expect it in other organs. I might expect it in the intestines. Like I wouldn't be surprised if they had, all their splanchnic tissues were bigger. So I wouldn't be so bigger. So in the intestines.
So pretty much when you consume the protein helps replenish the protein in your digestive systems and other things first before it goes into your muscle.
Yeah, I mean, intestines and liver get first crack at all amino acids except, the branch chains. So, but what was really interesting about this, the data that I don't have up here, is if you think about it, they were fed these diets for 11 weeks, and we measured all these. There was 120 animals in this study, and we weighed out, put together, and measured all the diets 3 times a day for every single animal. So that was a real pain in the butt, which is why we're not worried about this being repeated anytime soon, because we don't think anybody else is that crazy to want to spend 8 hours weighing out meals. But one of the things that was very interesting was that we showed differences in body weights and, actually this was part of, let me go back real quick. So we actually, along with that experiment, repeated this experiment over a long term, okay? So we fed these diets for 11 weeks, totally isocaloric, and showed differences in body weights, muscle mass, and body fat levels. Like wheat was way fatter than all the other groups, and whey was the leanest, okay? Well, whey and egg were the leanest. So it's funny because a lot of times, it gets into a totally different debate, is a calorie, right? You hear that all the time. Well, all we did was change the source of protein and change how it was distributed, and we saw differences. So I think that really points to the fact that a calorie a calorie is a calorie only in a bomb collimator, but your body is not a bomb collimator. So finally, looking at kind of distribution and how that's affected by things, we're also interested in the mechanism behind kind of how protein distribution is affected. Because so far I've only talked about kind of maximal responses to a meal. I've looked at all these responses that we're measuring are 90 minutes after a meal. Okay, so it's just a snapshot of protein synthesis. But the overall amount is the area under the curve, right? So duration's also important. If you could get protein synthesis lasting longer, that also is going to make you, better for your muscle. So there aren't a whole lot of studies looking at the duration of muscle protein synthesis, which is why my advisor told me to go look at it. So we took a meal that we knew would maximize the rate of muscle protein synthesis. So we got something that was well over the threshold, and we fed it to these animals. What we found was that the rate of muscle protein synthesis peaked at 90 minutes and was back to baseline by 3 hours. And I was like, cool. So when I go measure plasma leucine, it will go up and it will come back down and be back down by 3 hours. And that was exactly what I did not find. What we found was that plasma leucine went up and stayed up and was still elevated at 3 hours, even though muscle protein synthesis had returned to baseline. And I remember I ran that data probably about 3-4 times. And about, 4 months after the study, Dr. Layman came up to me and said, where are we with this duration thing? Because it's been a while since you did this study. I said, yeah, it's almost done. I'm just working on the data. I'm running it again. He said, didn't you run that like 3 or 4 times? I said, yeah, but it's wrong. And he said, well, why is it wrong? Is your technique bad? Are you getting variable responses? I said, no, it just doesn't make any sense. He said, well, that's not a good answer. He said, you need to stop trying to make your data fit your hypothesis and change your hypothesis to fit your data. Probably some of the best advice I ever got in graduate school. And I think a lot of fitness professionals could actually benefit from that as well. So we got, and one of the things we thought might be happening was, well, maybe the initiation factors that I talked about before, 4-ABP1 and S6K, maybe the signaling is starting to fall off. But that's not what we found at all. We found that signaling was still very reflective of plasma leucine levels. So what you have is you have protein synthesis falling back to baseline in the face of elevated leucine. Even though leucine is responsible for initiating the signal, it's not necessarily responsible for the duration of the signal. Okay?